This is what Newton, one of the pillars of physics, said about his life's work. I do not know what I may appear to the world, but to myself, I seem to have been only like a boy playing on the seashore and diverting myself in now and then finding a smoother pebble or a prettier shell than ordinary, while the great ocean of truth lay all undiscovered before me. The scope of physics is truly vast. While some scientists struggled with the big questions like our place in the universe, others have looked inward at the behavior of matter at the most fundamental level. For example, Rutherford's experiment showed us that atoms are composed of mostly empty space, completely overturning our intuition that they were dense and indivisible. Einstein gave us insight into the true nature of light, while scientists like S.N. Bose deduced the behavior of individual atoms and molecules at extremely low temperatures. C.V. Raman revealed what happens to light when it interacts with atoms and molecules in transparent materials. Each of these people, and hundreds like them, have helped mankind solve the puzzle of reality, one tiny piece at a time. One of the really fun things about physics is its relationship with technology. Each feeds the other. The discovery of fission in atomic nuclei paved the way for nuclear reactors. Attempts to understand the principles of quantum mechanics allowed the development of semiconductors, which led to the IT revolution, which in turn made new scientific breakthroughs possible. As we begin this journey into an exciting field, let us understand the lay of the land. Let us learn the vocabulary that we need to navigate this science. What are the fundamental forces? Actually, here is a better question. What is a force? Force is a weird term. You cannot really define this word outside of the effect it has on matter. A force can be thought of as an agency that causes a change in matter. It can be the position or the velocity or the shape or the rotation of a given body of matter. Forces can require contact, like touch. They may also operate at distance, like magnetism. Let's look at the fundamental forces and how they help us to analyze and express the nature of reality. Gravitation. We develop an understanding of how gravity works pretty early in our lives, usually through painful experiences. Anything that has mass in the universe attracts everything else that has mass with a force that bizarrely holds the universe together, even though it is the weakest of all the fundamental forces. Electromagnetic forces. The forces that are exerted by stationary and moving charges are known as electromagnetic forces. Just like gravity, electromagnetism can operate at a distance and decreases with distance. On the other hand, while gravity is always attractive, electromagnetic forces can be attractive or repulsive. Electromagnetic forces are stronger than gravitational forces by a factor of several billion, and it is in fact the reason we don't just vanish into thin vapor at the slightest persuasion. The strong nuclear force. Ever wonder why does a nucleus stay together? I mean, neutrons seem pretty happy with any company, but protons really hate each other. The repulsive force between like charges are very strong, so logically a nucleus should break apart without any help. The reason matter simply doesn't fall apart is due to the strong nuclear force that is 100 times stronger than the electromagnetic force. But the range of these forces is very small, so you don't really encounter them in daily life. Nuclear weak forces. It appears only during specific nuclear processes like beta decay, where nuclei break apart on their own. These forces have even less range than nuclear strong forces and yet are still stronger than gravity. While each of these forces we have just discussed arise from different sources and have different properties, there are still underlying similarities between them. It is these similarities that allow us to work out the nature of the universe itself. For example, the action of forces on matter, irrespective of the type of force, causes a change in the type of energy associated with the system. For example, when a stone falls towards the earth, the kinetic energy of the stone is increasing while the corresponding potential energy of the stone is decreasing. However, the total amount of energy, which is the sum of the kinetic and potential energies, remains constant. This unchanging quality of energy is called the law of conservation of energy. There are similar laws for mass and charge as well, which is why we call them conserved quantities. Another important feature shared by all fundamental forces is that they do not change with time. The laws that govern the universe do not care about the passage of time or its direction. In other words, if you ran the universe in fast forward or fast reverse, the laws of physics would remain equally applicable. This helpful property of fundamental forces is known as time symmetry. And if you decide to pursue physics at an advanced level, you will learn about this and other symmetries in more detail. Now that we have some idea of the quantities and phenomena we will encounter, we will next learn how to use mathematics to make sense of them and in turn to interpret our world in ways which are predictable.
Manorama Horizon. Learning made simple.